Page 54, we have these trig equations. Now, when we're solving trig equations, we're making use of our knowledge of trig identities. And to some extent, it's a requirement, but it also depends on the type of question you're being asked. Because if I'm asking you in the form of a multiple choice question to give me a solution, then you could use one of the techniques that we use on Desmos, just get the solution that way. And it's really pretty straightforward. But what I was saying last time, I know it was a week ago, so it's kind of like, I know you said stuff last time, but nobody remembers. We'll do it by hand, so you get the skill down, but then we'll also check it using Desmos and learn that skill also, because it's still valuable. All right. So when you look at something like number 3, where we have this idea that the sine of theta and the cosine of theta are not the same variable. All right. So one of them is treated like an x, the other is treated like a y. We need to get them to agree with one another. All right. And so the way we would handle that is by doing a conversion using one of the trig identities. So for example, we have a rule that says the sine squared of theta by definition is equal to 1 minus cosine squared theta. So I can swap out the sine squared theta for a 1 minus cosine squared theta. All right, that's one of our Pythagorean identities. So 3 parentheses, instead of the sine squared theta, I'm going to put a 1 minus cosine squared theta minus the cosine theta that's already there is going to be equal to 1. All right. It doesn't look like the situation's improving, but it actually is. We just have to do a little algebra. So I'm going to distribute the 3. We're going to have 3 minus 3 cosine squared theta minus the cosine theta that's already there equals 1. And then I just want to, because it's quadratic, and when you start mixing functions together, it's not always easy to see what you're up against. But when I see a power of 2, we're looking at something that is quadratic by nature. All right. So I want to get it into the appropriate form for a quadratic, and that would be highest powers come first and then decrease from there. All right. So I'm going to bring over the 1 by subtracting. We'll be looking at 2 minus 3 cosine squared theta minus cosine theta is equal to 0. But again, I want to have my highest power come first. So I would put the -3. I would take this piece, I'd take this one and put that in the beginning as a -3 cosine squared theta. Then I'd follow that up with this one, minus cosine theta. And then I'd put the +2 off at the end, right? Because that's our constant. All right, so I'd do a +2 off at the end is equal to 0. Now, if you're looking at something that's factorable, then go for it. But it's not always obvious that it's factorable, especially when you have a leading coefficient that's negative. So what I'm going to do here is I'm going to multiply the whole thing by a -1, just to kind of make it a little nicer. All right, so we'd be looking at 3 cosine squared theta plus cosine theta minus 2 is equal to 0. All right, so then from there, I'd want to be looking at the factor. Now, and maybe you don't want to factor, maybe you want to do the quadratic formula. We should always try to factor first, because if you can, it's going to just make things that much easier. All right, so if this is going to be factorable, it's going to involve a 3 cosine theta and a 1 cosine theta, or just cosine theta, because we have to get to a product. Let me use a different color here. We need to get to a product of 3 cosine squared theta. Since 3 is prime, we know it's got to be 3 times 1 to give you the 3, and cosine times cosine would give you a cosine squared. All right, Same idea for the 2, or at least the -2. I need to get a product of a -2. So it's got to be 2 and -1, or -1 and +2. It's just a question of placement. So do a little trial and error and see how that plays out. So if I put the 2 here and the 1 here, what I like to do is, this is going way back. I like to use this little arc approach, which is to say, I find the product of the outer and inner terms. 2 times cosine theta would be 2 cosine theta. 3 cosine theta times 1 would be 3 cosine theta. I would want to know how I can piece these two together through addition or subtraction in order to get just the yellow, just the +1 cosine theta, right? Because these two terms have to add to that middle. These two terms have to add to that middle term, right? The only way that that's going to happen is if the 3 is positive and the 2 is negative. And the only way that's going to happen is if this is a minus and this is a plus. Right? So on the outers, we get 3 cosine theta. On the inners, we get -2 cosine theta. Put them together, you get a 1 cosine theta. Right? What a lot of people will do is they'll take this expression here, just going right back to this one. They'll take that and say, okay, let me think of this as if it were -3x² minus x plus 2. They'd factor that, in a way that they're comfortable factoring. And then once they come up with those factors, they'll swap out all the x's for cosine thetas. That's another way you can think about it. Right? But once you have that, you have your 2 factors. Now you set those 2 factors equal to 0 and solve. You set each of those 2 factors equal to 0. So 3 cosine theta minus 2, that's set equal to 0. And cosine theta plus 1 equals 0. Yeah. I'm just going to shrinky dinky a little bit. All right, so we're just taking those 2 factors, setting them equal to 0, and solving for the value of theta. Easier said than done, of course, but that's what we're doing. All right, so for the first equation, I'm going to add 2 to both sides. We get 3 cosine theta is equal to 2. Then I'm going to divide both sides by 3. And you get cosine theta is equal to 2/3. The other one's much easier. Subtract 1 from both sides. Our goal, though, is to get theta, not cosine theta. So we get an extra step in each case. So we get cosine theta is equal to -1. Now, the domain for these questions, all of the questions on this page, are on the interval of 0 to 2 pi. All right, so I'm just going to jot that down there just as a little reminder to myself. But that's where our knowledge of the unit circle is going to come into play. All right, because in some cases, we can figure it out just by knowing the unit circle. In other cases, we're going to do a little bit extra, a little calculator work. All right. So for this one, this is the easier one. This is really just saying what angle on the unit circle has a cosine value of -1. All right, let me just grab my unit circle. Screenshot, no, I want to copy it. Just going to grab my unit circle for reference. Remember, cosine is the x value on your unit circle. All right, so the x value of -1 is what I'm interested in. That only happens at this one location. All right, it happens when when theta is equal to pi. All right, so we have a solution here. Theta is equal to pi. But I also have to address the other piece. All right, now using the same reasoning, I would have to say, all right, what value on the unit circle has an x, or what angle on the unit circle has an x value of 2/3. There isn't one. So I have to use a calculator approach here. So what I would do is take the arc cosine of both sides of this equation. So I would say arc cosine of cosine theta and the arc cosine, also known as inverse cosine, of 2/3. On the left-hand side, arc cosine and cosine cancel out to theta. On the right side, we got to do a little bit more. All right. And bearing in mind that most of the time when you're dealing with trig functions, you have multiple solutions. In the case of quadrantals, very often, and so anything that falls on an axis, x or y axis, very often you only have one solution, but most of the time you're looking at multiple solutions. So based off of our knowledge of ASTC, we can infer or just decide that we're looking for two solutions, or just know that we're looking for two solutions, because cosine is positive in two quadrants, in the first quadrant and the fourth quadrant. All right, so whatever I get from the calculator, if I type in arc cosine of 2/3, it'll give me a value. That value is in radians. All right. Now, the radian value is going to put you in the first quadrant. All right. The reason I know that is because 0 degrees corresponds with 0 radians. That's easy enough. 90 degrees corresponds with pi over 2 radians, which is approximately 1.57. Right? About. So we're looking at something that's roughly half that measure. So I don't know precisely where it would be, but I do know it's going to be somewhere in the neighborhood, roughly halfway between 0 and 90 degrees. Right? So it's going to be somewhere in this neighborhood. I don't know where it is, so I'm just going to plop it. Well, I don't want to plop it there, because that's a particular value. So I'll just kind of plop it like right there, for lack of a better place to put it. Right. So we would say that this is about 0.841 radians. Right. But I need that same reference angle in the fourth quadrant. So whatever that angle is, you're going to do the same thing, but going down into the fourth quadrant. Right, so this angle is still 0.841, but I need to know what the true angle is, not what the reference angle is. So the true angle would be this angle that I'm marking in red. So everything but the 0.841. So I could do 2 pi minus that 0.841, but I could also do 2 pi minus the arc cosine of 2/3. And that would give me my other result, right? So about 5.442. So those would be my two solutions for the more challenging part of the problem, which is the cosine of theta is equal to 2/3. So about 0.841 or 5.442 radians. So pi radians, 0.841 radians, 5.442 radians, all solutions to this problem, right? And that's a lot. So if a question didn't ask you to show all this work, and they won't all ask you to do that, but you got to be prepared to show the work. want to get a copy of this before I lock it in. So if it doesn't ask you to show all the work, that's good, because then you could go right to the Desmos approach, and that would bring you right back to the original problem. Right. So what I would do is type the left-hand side in as one equation. Right, new blank graph. I would type in y equals, do y or f of x equals, doesn't matter. But we're going to put our equation in terms of x. Right. Y equals 3 times the sine squared of x minus cosine x, then y equals 1. Left side in as one equation, right side in as another. The thing is, you get way more than you bargained for here. So there's two ways to handle it. One would be to only look at the interval from 0 to roughly 2 pi, which, 2 pi, 6.28 approximately. But it's kind of hard to tell where the end of that interval is. So what I do instead is I truncate my graph based off the domain. So open squiggly, 0 less than or equal to x less than or equal to 2 pi. Then it'll only graph the relevant part of the function. Now, the horizontal line I don't really care about, because once I truncate the curve, then I'm good to go. Any intersections are going to necessarily be part of the interval. Now I just tap on those intersections, and we get it all straight away. Pi, 0.841, and 5.442. Right? So definitely a whole lot easier to do it this way. But again, you find yourself sitting in a calculus class down the line, and they're like, what is this Desmos you keep referring to? And when you're in that position, it's like, well, what do you do? Well, do you just withdraw? No, you make the adjustment. So that's why I'm showing you all these different approaches. And I don't want you to get caught flat-footed down the line. Right? But they're not all, I've been showing you the crazy ones. Some of them are pretty easy. All right, 2 and 3 are like the examples of the crazy nasty ones. But 4 is an example of probably one of the easiest ones that you'll experience. Actually, super easy, barely an inconvenience. Because for this one, I would just add a 1 to both sides. Sine squared theta is equal to 1. I want to get a sine of theta alone, so I'm going to take the square root of both sides. Eventually, the square root of sine squared is sine. The square root of 1, when I take the active square root of a number, I'm going to get a positive or negative, so plus or minus 1. So then I bring my unit circle back into the party here. On the domain, because remember, all of these questions are saying over the interval of 0 to 2 pi. Right? That's all right up in the open here. Solve each on 0 to 2 pi. So in the unit circle, I'm just looking for any instance in which the y value is equal to 1 or negative 1. That happens in 2 instances. It happens here. It happens here. Right? So that tells me that my theta values, those are the only 2 instances. Theta would be equal to pi over 2 or 3 pi over 2. Right? But hardly any algebra to that one. But that's how it goes with algebra. The concept of factoring overall is not challenging. The concept of solving an equation overall is not challenging. It's when you run up against a particular problem that makes it challenging. That's when math becomes difficult, But sometimes they're that easy. Right? But this one, even this one is only easy if you have a unit circle handy. Right? Because If I go with this and I type in, for example, I try to do it using the arc arc sine. Maybe I forget the plus or minus one, but let's say I don't forget. I would type in the arc sine. You could use the inverse sine function also. I would type in inverse sine of 1. And again, that's the same thing as saying the arc sine of 1. You see, it's the same value. All right. It's going to give me the decimal value. So Desmos will convert over to fraction form if there's a fractional equivalent available, but it won't convert over to simplest radical form just because you want it to. Right? It won't convert over into an irrational number just because you want it to. Right? But if you have a suspicion that this is some multiple of pi, then what you do is you take this number, whatever this decimal is, divide it by pi, get that value converted over, and then slap a pi back on that. All right. But you'd also have to do it for the arc sine or inverse sine of -1. Now here you got to be careful because this is saying negative 1.57. All right. And the reason why it's saying that is because Desmos is adhering to the domain and range for inverse trig functions. All right. So, and I'll show you with the arc sine. It's the same deal. All right. So this is not on the 0 to 2 pi domain, but you can figure out what its coterminal angle would be on the 0 to 2 pi domain, because if this is telling you to go negative pi over 2, that's just telling you instead of going pi over 2 in the positive direction, go pi over 2 in the negative direction. Where would that put you on the unit circle? It would put you at 3 pi over 2. Right? So you could do it that way. But if you're going to go, and this is what the whole tech assignment's about, if you're going to go to Desmos to do the work for you, why not let it really do the work for you? Y equals sine, little back arrow here, squared, x minus 1, y equals 0. Pop in my domain just for the funkier equation. You do it for both, but you really only need it for the one. All right, so 0 less than or equal to x less than or equal to 2 pi. We got our two solutions here. You can see them. One right here, one right there. All right, let it do the work for you. Much easier if you have the choice in the math. All right. Now number 5 is kind of like the happy medium. Number 6 looks like it would be just a terrible problem, but it's actually one of the easier ones too. All right. But number 5 is kind of a happy medium because you have that secant function, which could be thought of as 1 over cosine. All right, so 2 cosine theta plus 1 is equal to 1 over cosine theta. Now, the first thing I'm going to do to solve this algebraically is I'm going to multiply everything by cosine theta. But in doing so, I'm going to lose a variable in the denominator. So I got to be careful. All right, this function is undefined when cosine of theta is equal to 0, right? Because that's the denominator of a fraction. We never want 0 in the denominator of a fraction. So if cosine of theta is equal to 0, then we'd have a problem. Now, cosine is the x value of any coordinate around the unit circle. So any x value of 0, any angle that corresponds to that, would cause this function to be undefined. All right. So that happens at pi over 2 and 3 pi over 2. So undefined when theta is equal to pi over 2 or 3 pi over 2. All right, so these are bad answers. So we want to keep an eye out and make sure that we don't get one of these. If we get one of these as a solution, we'd have to dismiss it. But that's also why the Desmos technique is so important, because if it doesn't show up as part of the Desmos solution, then it's not a solution. All right. So distribute, and really you're doing it to both sides. So let me actually get rid of those arcs. So 2 cosine squared theta plus cosine theta is going to be equal to 1. Bring the 1 over. You'll be looking at 2 cosine squared theta plus cosine theta minus 1 equals 0. And again, it's another factoring situation. And like I said, this is kind of like the happy medium, and I'll show you why in a sec. We have 2 cosine theta times cosine theta. If we're going to get to a negative 1, it's going to be 1 and 1. Just a question of which one's negative and which one's positive. All right. So for the outers, we're looking at 2 cosine theta as is. Inners, we're looking at cosine theta. If I want these two numbers, cosine theta and 2 cosine theta, to add to just the cosine theta, I would want this one to be positive and this one to be negative. In order to get a negative cosine theta, it's the 1 in that first binomial that needs to be negative, and the 1 in the second binomial should be positive. All right. But that's where things kind of ease up a little bit. Because when I set each of these factors equal to 0, I don't get the mess that I got with number 3. And the reason is, when I solve, I get cosine of theta is equal to 1/2. That's a unit circle ratio. I get cosine theta equal to -1, also a unit circle ratio. All right. When I got 2/3, right? When I got 2/3, it required me to do all this other stuff. But when it comes to unit circle ratios, it really is just picking it off of the diagram. All right. So now I'm just looking for any instance in which I have an x value of 1/2 or -1. So 1/2 happens here, which is pi over 3. It happens here, which is 5 pi over 3. And the other number was -1, which happens at pi. All right, so that gives me 3 solutions. So theta for this one was pi over 3 or 5 pi over 3. Theta would be equal to pi for this one. All right. Now we don't have any contradictions here. None of these numbers are pi over 2 or 3 pi over 2. So we don't have to worry about any extraneous solutions. All right. But this one was a whole lot easier because we don't have to worry about that inverse trig stuff with the domains and all that. All we had to do is pick it off of the unit circle. Right. But again, just popping it into Desmos will give you the answer too. So 2 cosine theta plus 1, so 2 cosine x plus 1. And then y equals secant x over the appropriate domain of 0 to 2 pi. So any intersections, you see the red one is truncated even though the blue one isn't. Any intersections that show up are necessarily going to have to be part of the correct domain. So as long as you truncate one of them, you're good. All right, so pi over 3, pi, and 5 pi over 3, just like we got algebraically or analytically. The last one on this page, tangent squared is equal to tangent. So it's quadratic because it's got a power of 2. I'm going to subtract off the tangent of theta. So tangent squared theta minus tangent theta is equal to 0. But we have a GCF here. We have a common tangent that can be factored out. All right. So you gotta kind of think of it as if it were t squared minus t. That would become t times t minus 1. All right. So instead of t, we're saying tangent. All right. It's a whole function. All right. set each factor equal to 0. Now, if you don't know the tangent ratios around the unit circle, you'd be totally forgiven. But you could still get the answer to this question pretty easily, and I'll show you why. All right. So, but first, I'm going to add the 1 to both sides. We're getting tangent theta is equal to 1. Now, for the first equation, well, tangent of theta is equal to sine over cosine. All right, so assuming you don't know anything about tangent ratios around the unit circle, we could convert it over to sine over cosine, cross multiply, and get sine of theta is equal to 0. All right, so the sine value is the y value around the unit circle. All right, so any y value around the unit circle is going to be what I'm looking for. I guess that's fine. So any y value around the unit circle equal to 0, I meant to say. So that happens here and here. All right. So our domain is from 0 to 2 pi, right? Including the 0 and including the 2 pi, the square brackets. So theta would be equal to 0, pi, or 2 pi. Any of those would be possibilities. All right. The other part's a little kookier, but still very easy, because tangent again is sine over cosine. You still cross multiply, put the 1 over a 1 and cross multiply, you get sine of theta is equal to cosine of theta. All right. Now that one's a little weird because it doesn't seem like you would get anywhere. It seems like, all right, we're at a wall here. There's nothing we can do. All right. No solution. You know, it seems that way. But really, when you think about it, if we know that around the unit circle, the cosine is the x value of any coordinate, the y value is the sine of any coordinate. I'm sorry, the sine is the y value of any coordinate. Then really all I'm looking for is any instance in which the x coordinate and the y coordinate are the same. Right. So if I have that in mind, then I'd be looking at this. That's an instance where the x and y coordinates are the same, pi over 4. Here, that it doesn't play out here because these are opposites of one another. Same thing over here. But over here it works. They're both negative. They have the same absolute value. They're the same numbers. Right? So we would get pi over 4 and 5 pi over 4. Or 5 pi over 4 or 5 pi over 4. All right, but still something Desmos can handle. It's just when you kind of deviate away from the sines and cosines, it starts getting a little funky in terms of what the graph looks like. But as long as you just kind of stay the course, it'll all work out. So I got tan squared of x, tangent squared of x, and then tan of x, or tangent of x. You see, it gets kind of messy, and it's kind of hard to tell what's going on. If anything, pop that domain in for the second equation too, just because it'll trim things down to the bare necessities. So yeah, it's a pretty ugly looking graph, but any intersection would be a relevant intersection. All right, so all these gray dots. So I got 0, pi over 4, pi, 5 pi over 4, 2 pi, all the ones that we came up with analytically. All right. But you could see just based off of this mess of a page that obviously this is the most complicated concept so far in this course. And it's just because there's so many moving parts. But to know that you have the means to come up with the answer without having to do any of this work, you know, like that's half the battle, just knowing how many solutions you should be looking for. If Desmos is going to tell you that, and not only that, tell you what they are, that's definitely a good thing. All right. So we're going to shift some gears here. We're going to talk about applications of trigonometry. So the law of sines and the law of cosines. We'll start with the law of cosines. All right. It's not a difficult process in terms of the application of the formula. It's just the formula itself is kind of funky looking, right? But let me just draw. I'm going to kind of take you through the theory, and then the application of it. Right. So the law of cosines starts off with this idea that we could solve triangles that are not just necessarily right triangles. All right. And it's going to involve inverse trig, which is the connection between this and what we've been working on. All right. But SOHCAHTOA is something that you should be familiar with. You know, like the right triangle ratios, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. But when it comes to trigonometry, and the root of trigonometry is trigon, which is another name for triangle, right? So it's the mathematics of triangles. Like there's certain things that you can figure out when determining metrics associated with triangles. You can figure out the lengths of sides, you can figure out angles, you can figure out areas, right? But they're not all necessarily going to be right triangles. So we have to make the assumption that we could end up, or we could be presented with a problem that we'll end up having to evaluate, and that problem might not necessarily be related to a right triangle. Okay, so we talk about a triangle that's labeled ABC. You can kind of label it any way you want, as long as you do it consecutively. All right, so working your way around. So I usually start with the lower left and work my way around in a counterclockwise fashion. But for triangles, it generally doesn't matter. It's when you get into quadrilaterals, that's when things get a little dicier. All right. In a triangle, the side opposite of an angle is named by the same letter, just lowercase. So this would be lowercase a, lowercase b, and lowercase c. All right. So the law of cosines, it's actually built off of the idea of SOHCAHTOA, right? So I'm actually going to show you one version of the law of cosines, like where it came from, and then I'll just give you the rest. But if you drop an altitude from that vertex angle C, and call it H for altitude, I already used A, so H for height, then we can develop some ratios, we can develop some measures, right? One thing that we could say is, for example, that I'm just looking for where I want to write this. I'll do it below, but I'm going to make it a little smaller. I can determine things like sine ratio or a cosine ratio or even a tangent ratio, right? But I would also need some way of coming up with the length of the base itself. Now I know the whole thing is C, but that doesn't tell me what these two missing pieces are, right? So what I would do, instead of just kind of hoping for the best, I would call one of them X, and it really doesn't matter which one I call X. I'll just call this one X. The other one is going to be C minus the value of X. Right? So we have information, it's just we don't have any conclusions to draw from this information. But what I can say is, because I have a right triangle here, I have a right triangle here, I could say something like x squared plus h squared is equal to a squared. All right, a little Pythagorean theorem. I also have SOHCAHTOA, like I was mentioning before. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If I go with the cosine is equal to adjacent over hypotenuse, and let's say I focus on just angle B, I could say the cosine of B is the adjacent side, which is X, over the hypotenuse, which would be A. Right, so that's a piece of information. All right. I could also do something, I can do something with this triangle here. I have, again, the Pythagorean theorem at work. I can say c minus x squared plus h squared is equal to b squared. I could also create another trig ratio from angle A, for example, but I'm just going to kind of leave it at this because we have enough to work with. Right? Because looking at just this first equation here, I can actually do a fair amount with this. Because I see here that I have an h squared, but I also have an h squared here. Right? So I can use some substitution to replace an h squared in one equation with an h squared with another expression. So if I take my x squared plus h squared equals a squared and solve it for h squared, so subtract off the x squared, I will get h squared is equal to a squared minus x squared. All right. So that would actually give me something to substitute in. I could say, you know, I'm just going to grab this other equation and bring it on up. Do a little copy paste action. I think I'm getting more than I bargained for here. Yep. I'll do that. Right, but I can now replace the h with an a squared minus x squared. So now I don't have the h anymore. I don't have to worry about the height. I would have to distribute this out. I mean, not ideal, but we'll do it. So c minus x squared is the same as c minus x times c minus x. And on to that, I have to add all this other stuff. So a little distributive property. I'm going to get c squared minus cx minus another cx plus x squared plus a squared minus x squared is equal to b squared. And it seems like this situation is getting out of control, but it's actually going to get really nice really quickly. Right? It just doesn't seem like there's any chance that that would be the case, but it is going to happen. Right? So these two terms can be combined. So I'd have c squared minus 2cx. I have a positive x squared and a negative x squared on the same side of an equation. They're going to cancel away. Plus a squared is equal to b squared. So if you remember, we started this all off by drawing a triangle with angles A, B, and C and sides A, B, and C. I then introduced the h and the x. If I can just get rid of that x, then I would have a formula that's exclusively in terms of A, B's, and C's. So if I have information related to just the sides and angles of any kind of triangle, without having to know what the altitude is, without having to know what each piece of the base is, then I could solve that triangle using this new rule that we're inventing. All right, and that brings us back to this expression, because if I put that cosine b over 1, I can cross multiply. X times 1 is x. A times cosine b is a cosine b. So I can actually swap out that x for an a cosine b, and we would be left with c squared minus 2c times a cosine b plus a squared is equal to b squared. All right. Now all we'd have to do is kind of clean it up just a smidge, just move some things around, and we have one variation of the law of cosines. All right. So if I put the a squared and the c squared together, I could say a squared plus c squared minus 2ac cosine b. So 2ac times cosine b is equal to b squared. That's one version of the law of cosines. Right? There's actually three versions, but we just, using algebra, discovered one of them. The whole idea is that you would never want to have to do this every single time. You'd rather just jump right to the formula that's going to give you your answer. Right? So the law of cosines, it's actually the laws of cosines. There's three of them. I'll say rules. We have a squared is equal to b squared plus c squared minus 2bc times cosine of a. B squared, that's the one we just came up with, is equal to a squared plus c squared minus 2ac times cosine of b. And then the last one would be c squared. This is a lowercase c squared, and my lowercase and uppercase don't really distinguish themselves. A squared plus b squared minus 2ab times cosine of c, capital C. All right. So these three components here, these are all angles. Everything else are sides. Right? But this is the law of cosines. Applying it is pretty easy. Number one, suppose a triangle ABC has side A equals 4, B equals 7, and angle C is equal to 54 degrees. What is the measure of side C? Right? So I'm going to use the version of the law of cosines that'll solve for side C. But really, the law of cosines is more easily identified, which one you use based off of the known angle. So it's because, it just so happens we're looking for side C, but it's because we're given angle C. That's why we select this version of the formula. All right, c squared is equal to a squared plus b squared minus 2ab times cosine of c. So we don't know our unknown side c, so c squared is equal to 4 squared plus 7 squared minus 2 times 4 times 7 times cosine of 54 degrees. All right. Coming up with the law of cosines, Desmos, is not the most challenging thing in the world, because, if you just put in the formula pretty much as you see it, it'll just kind of spit out what you need. The only thing is that if you wanted to solve for C, then you would want to take the square root of the whole thing. So C is really going to be equal to the square root of all of this stuff. All right. So what you could do, if you want to have something, and I'll like I've been doing, I'll put this on Blackboard for you. But I could put in C equals the square root of a squared plus b squared minus 2ab times cosine capital C. And then get a slider for each one of those pieces and it'll spit out your answer. The thing is, you got to be careful about, well, a lot of things you got to be careful about, but one thing in particular is this is only going to give you C, side C, dependent on angle C, right? You still need the other two variations, but also this Desmos is in radian mode. These answers are calling for degree values. So I would want to convert this over to degrees. My A value is a 4. My B value is a 7. Now these are sides of a triangle. There's no reason why we would have any negative values involved here. So when I'm setting up my parameters on the low end, I'd make those both 0. So I don't ever have to worry about having anything negative. And then same thing for the angles. You think about what the largest angle you could have in a triangle would be. It's probably somewhere around, like you can have an obtuse triangle. So somewhere in the high 100s, but no more than 180, so my C value could never be equal to 180, but it's probably not even going to be close to 180. All right. So, but 0 to 180 is a safe domain for your angles. So then 54 is the angle that they said. I just got to get it to lock in. And then once I do that, it'll spit out my answer. They said anything about rounding? No. So C is approximately, I'll say 5.7, just 5.7 because they didn't give us any units. All right. Now, number 2 says, suppose a triangle XYZ has the sides of 5, 6, and 7. What's the measure of the angle across from the side of measure 6? So it's like right into the fire. We're doing everything with A, B's, and C's. Now all of a sudden it's X, Y's, and Z's. Well, it's really not that bad because they say X, I say A. They say Y, I say B. They say Z, I say C. All right. So we'll treat this like an A. We'll treat this like a B. It really doesn't matter. And we'll treat this one like a C. All right. So the X value, which would be the side opposite the X angle, would be 5. So that's my A, my lowercase a. Across from the Y would be the 6. That's going to be my lowercase b. And then across from the C is 7. Across from the Z is 7. So that's my de facto C value, my side C. All right. So they're saying, what is the measure of the angle across from the side of measure 6? Well, they're asking for the Y, but really we could think of that as the B. All right. So I need the version of the law of cosines that involves angle B. So B squared is equal to A squared plus C squared minus 2AC times cosine of B. All right. Now for this, they're asking us to figure out the angle. So what I would actually do, if I'm thinking in terms of Desmos, if I wanted to create a rule here, what I would do is solve this general equation for B and then let Desmos do the work for every problem that comes after this. All right. So subtract off an A squared, subtract off a C squared from both sides. So I'd have B squared minus A squared minus C squared is equal to negative 2AC times cosine B. I want to get the cosine of B alone, so I would divide out the negative 2AC, divide out a negative 2AC. So I'd have cosine of B equal to, well, this whole expression, right? Now that's cosine of b. I want just b. Right? If I want just b, I have to take the inverse cosine or the arc cosine of both sides of this equation. All right. So I'd be looking at arc cosine of all of this would be equal to the arc cosine of the cosine of b, which in turn is just going to give me b, capital B is equal to all of this stuff. So I have a rule that'll help me figure out angle B, right? A general rule, which is good. That's kind of where we want to be, right? So it's just a question of how you want to put this in. I mean, you want to create a brand new Desmos for just the angle. I mean, that's probably not the worst idea in the world, you know, but I could also just kind of plug and chug away here. I'll just do it all in one shot. I'm going to get rid of this and just type it in from scratch. And I'll put a nicer one up on Blackboard later, but I would type in arc cosine open paren b squared minus a squared. Oops, stay up top. Minus a squared minus c squared over negative 2ac. But give me all my sliders, all my necessary sliders. I still want to make sure that I'm in the appropriate mode, right? I should be in degree mode. I could call that equal to capital B if I want, but that's not really necessary, right? The values that are important here are the a value of 5. Right, the a value of 5. Right, a value of 5. A value of 5. The b value of 6. And the c value of 7. All right. And so it'll spit out the answer. All right. So it'll say B is approximately 57.1 degrees. Right. I mean, you could have plugged and chugged away from this, you know, plugged the numbers in right away and solved it. But coming up with a general rule is always going to be preferred because then you don't have to reinvent the wheel every single time. Right? So now I know that if I'm given an A, B, and C value, I can figure out angle B. I could also figure out angle A and angle C. So I can call this B equals. I can do a little duplication, you know, just by swapping up some of the letters. Right. So if I want to find angle C, really, I mean, it's working with this formula, but if you look at it, it's going to have the same general structure, except it's going to be c squared first. So c squared minus a squared minus b squared over 2ab. And then you could do the same thing, finding angle A, B, C. So angle A would be really the same general idea, except a squared minus b squared minus c squared. You're just swapping some letters around, that's all. Right. Over 2bc. So you'd have angle A, angle B, angle C just by knowing sides A, B, and C. All right. Now, if these three angles add up to 180, then we're in business. All right. Angle A plus angle B plus angle C should equal 180 degrees because there's 180 degrees contained within a triangle. All right. So we're in very good shape here. All right. So now we got a Desmos that's ready to rock and roll to figure out the angles given the sides. All right. So let me say, save law of cosines. Finding angles. Just some kind of placeholder title. But yeah, so now we have a calculator that's going to do it for us. All right. So if I know, like for example, back to number one, we solved for the missing side C, but we knew A was 4, B was 7, C we said 5.7, or we determined 5.7. So I just pop that in. It'll let me. Come on. Come on. Okay. All right. So I have angle A, 34 degrees, 35 degrees. Angle B, 90-ish degrees. It's kind of freezing up on me. And angle C was about 54.5 degrees. All right. So, you know, a little error due to rounding, but you know, it's in the right neighborhood of what it was supposed to be. They said 54. We came a little bit more than 54. So pretty solidly right in the neighborhood. All right. Let me just pause for 1 second. Resume. The last thing we're going to talk about is the law of sines, an area of a triangle. We might just do only law of sines tonight, but it's a little easier to derive this rule. I'll show you. Poor quality diagram. Same idea as before. We drop an altitude. H for altitude. Altitude. Again, SOHCAHTOA is a thing. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But this time we're going to focus on the sine ratio. All right. So I'm actually going to draw multiple triangles here. I'm going to duplicate this and move some angles around. So we can come up with ratios from these two triangles. And again, all I did is I just moved some things around. All right. So although I kind of want it to be a little bit more accurate to what it's supposed to look like, let me just rotate real quick. Something like this. I'm actually going to put A at the top. So I rotated it. B would be over here. C would be over here. And then I'll drop an altitude. Something like that. All right. So we can come up with a ratio here, and this ratio would be the sine of angle A would be the opposite of angle A, which would be H, over the hypotenuse, but that hypotenuse is dependent on whatever we call this angle. So opposite side B, angle B is side B, opposite angle A is side A. So I would say the sine of angle A is the opposite over the hypotenuse. Sine of A is equal to H over B, right? Now I can take that and I could solve it for H, right? So I would say, if I cross multiply, H times 1 is H is equal to B times the sine of A, right? I could do the same thing from the perspective of B. So the sine of angle B would be equal to H over its hypotenuse, opposite over hypotenuse, H over A. So I would say, by the same algebraic technique, H is equal to A times the sine of B. Right, so that actually addresses the first triangle. Now the second triangle, I can kind of do the same thing. It's a different H, but it's the same idea. This would be C. I have an H, this would be a B. Right, so I could say the sine of B would be H over C, which makes H equal to C sine B. I could say the sine of C, opposite over hypotenuse, would be equal to H over B, which means H equal to B sine C. All right. Now it's kind of an apples and oranges situation here because these two H's are different H's. They're not equivalent to one another. So it's not a direct substitution. But what I can get is a relationship between these two equations, because if they're both equal to their own H, then they're equal to each other. So that tells me that B sine A is equal to A sine B. And same idea over here, even though it's different H's from the first pair, these two H's are equal to each other. But now I can conclude that C sine B is equal to B sine C. All right. Now, at first glance, it doesn't seem to be overly useful, but there's a lot of good stuff here. All right. So just focusing in on that first pair. If I take, and I'm actually going to give myself a smidge more of space here. If I take both sides and divide them by the sides, the two sides, A, B, I get a ratio, right? Because the B's would cancel, and I'd have sine of A over A. And in this case, the A's would cancel, is equal to the sine of B over B. Then in this instance, divide both sides by the two sides, divide both sides by the sides. And those two sides are B and C. The C's would cancel, telling me that sine of B over B, and over here the B's would cancel, is equal to the sine of C over C. All right, so I get a relationship here that is the basis of the law of sines, because I can say now the sine of A over A is equal to the sine of B over B. And the sine of B over B is equal to the sine of C over C. Therefore, if this is equal to this, which in turn is equal to this, then all three have to be equal to one another. Sine of A over A has to be equal to the sine of B over B has to be equal to the sine of C over C. All right, and that's our law of sines. It's actually one of the more interesting sort of derivations, because that idea of just changing the orientation of the triangle kind of makes it all work. But this actually gets at the area of a triangle formula, which, you know, like I said, it might be kind of a different story for a different day in terms of applying it. And in fact, I don't think, I'm looking at the clock, I don't think we're going to do any examples, but I will show you where the formula for area of a triangle comes from, because it's actually kind of cool. But yeah, we'll leave the examples part of it for next class. All right, so if I look at just any triangle, and you know, I could go right back to this whole scenario. And just kind of get all the fluff out of here. Area of a triangle, as we all know, is equal to half the base times the height. Or base times height over 2 if you want. All right. But what happens is we don't always know what the height is, but we may know some dimensions of the triangle. Like, for example, we may know some angles. It's not a right triangle, but we know a couple of angles. We know a couple of corresponding sides, but we don't know the height itself. Right. But what we have here are 4 different ways, here, 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 and here, to represent the height of the triangle. Right. So the base, that B value, I'm gonna revise what I wrote here. I'm gonna write that as the full word base, so as not to be used with side B, but the H is still H, right? So the base itself in this triangle has a length of C, right? Because it's opposite side C. I'm sorry, angle C. So the base in this triangle would be C. The height in this triangle, because remember, these ratios came from this triangle, right? So either definition of H would be satisfactory, right? So I can replace this H with either a B times the sine of A, or I can replace it with an A times the sine of B. Which gives us 2 new rules for the area of a triangle, right? 1/2 BC sine A, right? If I kind of clean this up, I'm going to shrink it down a little bit. Right, so 1/2 BC sine A we could say 1/2 AC sine B. But then if we just kind of follow that trend, it's like, well, what's the only possibility that's left? The case where, well, we have an angle A, we have an angle B. You'd be like, okay, well, what about angle C? What about the situation where there's an angle C? All right, well, let's do that. We could say 1/2 something something sine of C. But if you think about the sides that are used in the formula, we have angle A, whatever sides are corresponding with the other angles are the ones that are used. We have angle B, the sides that are corresponding with the other angles are the ones that are used. So we ignore side B and we use only sides A and C. So in this case, we would ignore side C and use only A and B, right? So what we now have are three distinct rules that would help us determine the area of a triangle, even if that triangle has an unknown height. So I don't know the height of the triangle. If I know two sides and an angle, as it turns out, the two sides and the angle in between those two sides, then I would be able to figure out the area, right? So if you kind of look at the breakdown, like for example, 1/2 AB sine C. So here's A, here's B, and here's angle C. You notice how the angle itself is captured in between the two sides, right? If it has that SAS relationship, side angle side relationship, then you could figure out the area of the triangle, right? But like I said, looking at the clock, I don't know. I mean, because these examples, they kind of take a little while because they're not quick and easy. They're actually pretty lengthy. Yeah. Kind of hung up. I'm hung up on myself here. You know, I'll do at least part A of this one because I don't want to leave you with nothing. So, but I won't take too much more of your time.
Professor, this is a lot. This is not nothing.
I know.
There is a lot going on right now.
Oh, just wait.
Should I be nervous? Like, this is ridiculously hard to like follow. Am I crazy?
Not crazy.
No, you're not crazy. I'm scared. Okay. I'm scared for the next test. I'm not gonna lie. I know that like I'm taking up class time. I'm sorry, but like this is scary. The last few things that we did, I was cool. But like now, I don't know.
It takes a little getting used to, but
yeah,
we'll work through
it takes some time to get used to.
Okay.
So this says, you know, a triangle DEF, but again, we're going to think of it as ABC. All right, so they're saying angle B is 29 degrees. Angle E is 112 degrees. And side D, all right, that's the one that's opposite angle D, is 22. All right. So it says solve the triangle. Now, when they say solve a triangle, they're saying find all missing sides and angles. All right. Finding the missing angle is not a big deal because if there's 180 degrees in a triangle and you know two of the angles, then it's just a matter of subtracting. So I would do 180 minus 29 minus 112, and I'd get 39 degrees. So that part, that shouldn't be much of an issue, right? But we do need to find the missing sides, all right? So we know side A, quote unquote side A. We need to figure out side C and side B. So it's just a question of what technique makes the most sense. Now, since this problem is on the sheet that's called Law of Sines, it makes sense that the Law of Sines would come into play. So what I'm going to do is I'm going to grab my Law of Sines formula here. All right. Now we know all the angles, so we're in good shape there. So sine of angle A would be sine of 29 degrees over side A, 22. Sine of angle B, well, we know B is 112, so 112 degrees over lowercase b because we don't know that. Sine of C, that's sine of 39 degrees. Again, unknown C. All right. So we have a compound equation here. But the good thing about this is we don't need to work with all three pieces at the same time. We can take two pieces and work with just those two pieces. Any two pieces of this equation, this compound equation, would be equal to one another. So what I could do is I could just grab, for example, these two pieces. Pull that out and look at that as its own equation and solve that. All right, so it's going to require a little cross multiplying, but your best bet, just to keep things clean, would be to cross multiply with it in its current form. So without figuring out what the sine of 29 is. Save the part where you figure out what the sine of 29 and sine of 112. Save that for the very last step. So when you cross multiply, this is going to be b times the sine of 29 degrees is equal to 22 times the sine of 112 degrees. If I want to get b alone, I would just divide both sides by the sine of 29 degrees. So it would cancel completely on the left, leaving me with just the b. But on the right, I could just pop that into Desmos, just make sure you're in degree mode. All right. So as a fraction, I would say 22 sine of 112 over sine 29. Now he said nearest tenth, so this would be 42.1. All right, so I know side B now is 42.1. All right. He said solve the triangle, so if I label up the triangle, I have the solution, so we're good there. Whether I have quotes around letters or if I just work with D, E, and F, that's fine. Either way, it doesn't make a difference. All right. But just like I did to find side B, I would do the same thing to find side C. I'm just going to choose two different pieces of the law of sines, right? I always want to incorporate the known ratio, the one that doesn't have any variables in it. I always want to get that into the action, right? Because one thing I wouldn't want to do, I don't want to take these two because then I'll have an equation with two variables. I only want a single equation with a single variable. So what I'm going to do is I'm going to set the sine of 29 over 22 equal to the sine of 39 over C, and then just do the same thing I just did. All right, cross multiply C times the sine of 29 is equal to 22 sine 39. Then divide both sides by the sine of 29. And that's going to give me side C, but I still got to do the crunching. But it's just a minor adjustment on the previous calculation. Instead of sine of 112, I'm going to say sine of 39 over sine of 29, which is going to give me 28.6. All right, and so that would be actually the solution to the triangle, which is, in terms of computation, it's a lot easier than the law of cosines. But, you know, there's a lot going on, right? And it does take getting used to. But once you have all this information, coming up with the area, and now I kind of feel like I should do that. Right? So coming up with the area is just a matter of choosing one of these formulas. It doesn't matter which one because I have the entire triangle solved for. Right? So choose one. Area is equal to 1/2 AB sine C. 1/2 AC sine B, or 1/2 BC sine A. Right? It doesn't matter which one you choose because you know all the sides and angles of the triangle. All right, so whichever one you choose, I mean, you might get some slight variation in your final answer, just some little decimal values, but when I make an answer key and I'm grading test papers, I have all the different variations of the correct answer, so I can give full credit regardless of what you come up with, as long as it matches one of the correct answers. All right, so I'm gonna go with, I'll take this one, it doesn't matter. So area would be equal to 1/2 my A value is 22, my B value 42.1 times the sine. Oh, I'm sorry, the C value is what I said I was going to use. All right, so 28.6 times the sine of my angle B, which would be 112 degrees. All right, and that just goes right into Desmos. So 0.5 times 22 times 28.6 times the sine of 112 degrees. Just again, making sure that you're in degree mode, you're looking at about 291.7. And that would be square units. They didn't give us any units, so, but for area, we want to make sure that they're square units, whatever the units are. All right, so 291.7. And I could show you really quickly, if I had done something, if I had done 1/2 AB sine C. So if I did this one, for example, it would be 0.5 times the A value, which is 22, times the B value, 42.1, times the sine of angle C, which would have been 39. You see, it's decimal points away. It's roughly the same thing. All right. But I would allow for either of those because they're both based off of a correct technique. All right. So yeah, like I said, it takes a little getting used to, but you get a handle on it pretty quickly once you start diving in. There's a lot on the next page in terms of examples. If you were to do all of them, it would take you a while, like a while. So I'll just suggest that you do numbers 1, 2, and 3. So we'll start off class next time going over those 3 problems, and then we'll kind of table the topic, and I'll give you more time to try numbers 4, 5, and 6. But then we get into just a couple of word problems, which really aren't that difficult. They just seem difficult, and then we touch on conic sections to round out the course. Right. So yeah. Let me stop the recording.